We have seen that complex magnetic textures emerge at the boundary between two homogeneous magnetic domains. Depending on the energetics and the shape of the magnetic field, we can obtain block walls, nail walls, skyrmions, merons, and so on. In the present part, I would like to understand how these structures can be moved when we apply an external force. I will first explore the motion of a one-dimensional domain wall, and I will see that depending on the compromise between disorder, applied force, and thermal activation, I can obtain completely different transport regimes. After that, I will focus on the motion of localized structures like vortices, bubbles, and skyrmions. And finally, I will say a few words about applications.
So let me consider this one-dimensional block wall. When I apply the magnetic field along the perpendicular direction, the domain with magnetic moments pointing up shall expand, and the domain with magnetic moments pointing down shall shrink. So based on Landau-Lifshitz-Gilbert equation, the magnetic moment at the center of the wall initially experiences two torques: the regular field torque that induces the magnetic moment to precess around the magnetic field, and the damping torque that pushes the magnetization towards the magnetic field direction. Remember that here gamma 0 is defined positive. These torques will induce the magnetic moment to tilt away from the block configuration. This tilt triggers the onset of the demagnetizing torque. Let's see how it works. Under the field torque, the magnetic moment in the center of the wall is precessed by a small amount towards the wall direction. That's the orange arrow here. In this new position, the magnetic moment experiences four torques: the field torque and the damping torque, but also two new torques due to the demagnetizing field. As a matter of fact, because the magnetic moment is tilted away from its rest position, it accumulates charges along the direction of the wire, and as a result, it experiences a reacting torque that lies along the damping torque, as well as a dissipative torque that competes directly with the field torque. While the field torque tries to take the magnetic moment away from its block configuration, the damping torque due to the demagnetizing field tries to put it back. Therefore, as long as these two torques compensate each other, the tilting angle of the magnetic moment is fixed and determined by the balance between these two torques. The resulting wall is in an intermediate configuration between a nail wall and a block wall, and the domain wall is in a steady motion only driven by the green and purple torques. If the external field is larger than the damping torque due to the demagnetizing field, the magnetic moment precesses around the external field. Its azimuthal angle is not constant in time anymore, and the domain wall enters a precessional regime. To describe these dynamics in more details, I could use the Landau-Lifshitz-Gilbert equation and solve it for rigid domain wall. But I won't do that here, because that's too easy. So I'll go the hard way and consider the Lagrangian formalism. This is a very powerful formalism that enables the description of complex dynamics by describing the system in terms of collective variables. Let's see how it works. By definition, the Lagrangian is the difference between the kinetic energy and the potential energy, integrated over the volume. The kinetic energy of a ferromagnetic system can be computed from the coupling between the magnetization current and the vector potential associated with the magnetization. Long story short, it looks like that. The potential energy is composed of the usual suspects: exchange, perpendicular anisotropy, demagnetizing energy, and Zeeman energy. In spherical coordinates, I get this familiar expression. Now, to determine the equation of motion of the magnetic domain wall, I will use the Euler-Lagrange equation that connects the partial derivative of the Lagrangian with respect to a given variable with the time and spatial derivatives of the Lagrangian. The last term in this equation is called the Rayleigh dissipation functional and accounts for all the terms that do not conserve energy. In our case, it boils down to the magnetic damping and looks like that. To solve the Lagrangian equation, I now assume that the profile of the magnetic domain wall does not deviate too much from its static solution. So I'll assume that the azimuthal angle only depends on time, and that the polar angle adopts the form we derived in the previous lecture, except that now the domain wall width depends on time, and the center of the domain wall shifts rigidly by Vt, V being the domain wall velocity, T being the time. We're going to assume that the velocity is constant in time. So in a nutshell, the collective variables of my domain wall are the azimuthal angle, the domain wall width, and its velocity. I inject this form into the Lagrangian defined above, integrate over space, and take the appropriate derivatives to construct the Euler-Lagrange equations for the three collective variables characterizing my system. I obtain this set of equations where Hk is the dipolar anisotropy energy. I can combine the first two equations to determine the velocity and azimuthal angle, and based on these results, I can use the last equation to determine the domain wall width. We obtain an explicit equation of motion of the azimuthal angle here. Now let's try to solve it. First, consider the condition for steady motion. In this limit, the time derivative of the azimuthal angle is 0. And the azimuthal angle is determined by the ratio between the applied magnetic field and the dipolar anisotropy multiplied by the damping. Therefore, the domain wall velocity and width can be obtained explicitly. Most importantly, the velocity is inversely proportional to the magnetic damping, which is a characteristic feature of the steady motion. Consider now the case when the applied field exceeds the critical field, alpha times hk over 2. In this case, the time derivative of the azimuthal angle does not vanish anymore, and the domain wall enters the precessional regime. In this precessional regime, the azimuthal angle has a complex dependence, but overall, one can assume that the time average of the function cosine phi times sine phi is 0. Therefore, the time average velocity is given by alpha delta times h. In other words, the mobility of the domain wall is much smaller in the precessional regime than in the steady regime. Let us now look at what happens in real life. The left graph gives the velocity of a domain wall computed numerically by X.R. Wang, and on the right, the experimental observation by Geoff Beach. The two regimes we just discussed appear clearly, the steady motion and the precessional motion. You see that indeed the velocity in the steady regime is much larger than the velocity in the precessional regime, and the velocity is constant over time as indicated in the yellow inset of the left figure. In the precessional regime, the azimuthal angle changes over time, resulting in a transformation between block and Néel configurations that results in an oscillating velocity, as indicated in the orange inset. The boundary between these two regimes is called the Walker breakdown and characterizes the so-called intrinsic pinning of the magnetic domain walls. An important question that has been around for some time is how to cancel or push the Walker breakdown limit. Since the velocity of the domain wall in the steady motion regime is much faster than in the precessional regime, it would be great to find a way to extend the steady regime as far as possible. I present here two solutions that have been recently proposed in the context of current-driven domain wall motion. Ricardo et al.'s team proposed to use a cylindrical nanowire. In this system, the domain wall is transverse, as indicated in the picture, and a continuous precession occurs. Since the cross-section is cylindrical, this precession does not cost any energy, and no Walker breakdown occurs. Alternatively, Hélène Gomonai has proposed to use an anti-ferromagnetic domain wall. Now, the drive is a staggered magnetic field. namely a magnetic field that changes direction on the two antiferromagnetic sublattices. This peculiar form of the torque exists in certain classes of antiferromagnets, as we will see in a future lecture. In this particular case, the very large antiferromagnetic exchange dominates the dynamics and no dipolar interaction exists. Therefore, no wall-to-nail transformations occur and the Walker breakdown is completely removed. The model for one-dimensional rigid domain wall motion works well in principle, but it is very difficult to find actual systems in which one can see the transition from the steady motion to the precessional motion. The reason is that magnetic defects are always present, and the pinning force coming out of those defects is usually much larger than the intrinsic pinning from Walker breakdown. Therefore, one usually observes two main regimes. At large external field, the force applied on the domain wall dominates over the extrinsic pinning and one obtains the flow regime, usually precessional. In contrast, at small external field, the disorder is so important that the domain wall occurs through thermal activation. One can distinguish two main regimes within the disorder-dominated region. At intermediate forces, you will find the thermally activated regime where thermal fluctuations assist domain wall depinning by the external force. In the limit where the applied force is even smaller than the pinning force, thermal activation results in a creep motion of the wall. The domain wall acts like a flexible membrane that hops from side to side in a creepy manner. So if I summarize this discussion on a chart, that's what I get. On the abscisse, I have the applied force, that can be an external field, a field gradient, or a charge current, and on ordinate, I have the velocity of the wall. I can distinguish four regimes: the creep regime, the thermally assisted depinning regime, the steady motion, and the precessional motion. As we discussed already, the steady and precessional regimes are separated by the Walker breakdown, and the creep and thermally assisted depinning regimes are separated by the depinning threshold. But most importantly, the disorder-dominated and the flow regimes have very distinctive features. While the flow regime is controlled by microscopic quantities such as the magnetic anisotropy and magnetic damping, the disorder-dominated regime is characterized by universal scaling. Moving from the disorder-dominated to the flow regimes passes by a universality breakdown. Here is a concrete example of an experimental observation. This plot has been obtained by Gorchon and coworkers and showed the velocity of a perpendicularly magnetized domain wall in ultra-thin platinum-cobalt platinum trilayers for different temperatures. It focuses on the disorder-dominated regime. The authors identify three regions where the velocity obeys universal scaling: the depinning region, the thermally assisted flux flow regime, and finally, at very small magnetic field, the creep regime. I won't enter in the details of all these regimes, and I will only focus on the creep regime as an example of disorder-dominated domain wall motion. In this regime, the disorder is very strong, and I can model the domain wall as a one-dimensional elastic membrane of length L and displacement U. The free energy is given here. It is composed of three terms. First, the elastic contribution, that is a product between the linear energy density of the domain wall times the square of the displacement U. This energy term states that the membrane gains energy when it extends over a distance U. The last term is simply the external force that applies on the displaced magnetic volume. And the most important term is actually the second one, which measures the pinning strength due to disorder. In this expression, psi is the correlation length of the disorder, and delta is the effective pinning strength felt by the membrane. Delta is proportional to the square of the pinning force, the density of pinning sites, and the correlation length. The square root in the free energy comes from the fact that only the fluctuations of the spinning strength influence the domain wall free energy. So we have three terms: elastic energy, disorder, and applied force. From these three terms, we can define some characteristic scales. For instance, the locking length is defined as the length for which the elastic energy for displacements of the order of the correlation length equals the disorder energy. You can understand the locking length as the characteristic length over which the membrane behaves rigidly. Eventually, the membrane can be seen as a chain of rigid membranes of typical length LC. The depending field is defined as the field at which the energy compensates the disorder strength. Above this field, the applied force exceeds the pinning due to disorder, and the domain wall enters a thermally assisted depinning regime. Finally, the depinning temperature corresponds to the elastic energy. Thermal activation overcomes the pinning barrier at this temperature. We have three characteristic distances in our system: the magnetic domain wall width, the disorder correlation length, and the locking length. Before we move forward with this model, we need to make sure that these distances are well separated. As a matter of fact, to be able to model the domain wall like a one-dimensional membrane, the domain wall width must be much smaller than any other length. Then, in order to derive a universal scaling law, the disorder correlation length must be much smaller than the locking length. Vincent Joly's team has extracted this scaling length in three typical systems as a function of the temperature. In platinum cobalt platinum, the domain wall width is around 10 nanometers, the disorder correlation length is around 20 nanometers, and the locking length is a bit larger, around 30 to 50 nanometers. So we are not talking about orders of magnitude differences, but these lengths are still well separated. We have something similar for nickel cobalt, as well as for gallium manganese arsenide. In all these systems, the scaling lengths seem well ordered, and one can, in principle, apply the model discussed above. So we now have a basic framework. Let's work it out. To solve this model, we need to first determine the manner the displacement depends on the length of the membrane. Of course, the longer the length, the larger the displacement. So one can guess a general scaling of this form, where zeta is a universal exponent. This assumption allows for writing the elastic energy explicitly, thereby obtaining an expression for the free energy. Now, if I want to obtain the relation between the membrane length L and the applied field H, I simply minimize the energy with respect to L, and I obtain the explicit relation I'm looking for. Reinjecting this length into the free energy, I end up with the expression of the free energy as a function of the external field. Once I have the free energy, I can estimate the domain wall velocity. To do so, I will assume that the depinning probability follows an Arrhenius law, which gives a velocity with this general form. Here mu is a critical exponent that is dictated by the relation between the membrane displacement and the membrane length. The last question that remains to be answered is the value of this critical exponent mu. This exponent depends on the class of disorder involved, long range or localized, as well as on the dimensionality of the system. The class of problems that corresponds to the creep motion of magnetic domain walls in ultra-thin magnetic multilayers is called the two-dimensional Edwards-Wilkinson universality class, which considers an elastic membrane in a thermal noise. This universality class is defined by a critical exponent zeta equal 2/3, which yields a creep law with an exponent mu equal 1/4. This law can be verified experimentally by tracking the relationship between the velocity and the external field of magnetic domain walls in ultra-thin perpendicularly magnetized films, such as platinum cobalt platinum. This picture is a magneto-optical Kerr image of such a motion. The two plots here report experimental data. The left one is taken from the seminal work of Lemaire and co-workers, where they record the velocity as a function of the external field over several orders of magnitude. This is actually one of the difficulties that arise when studying creep motion. One necessarily needs to span domain-wall velocities over several orders of magnitude to confirm the power law. You see here that when plotted in logarithmic scale, we obtain a very nice relation with the inverse of the field, power 1/4, confirming the model discussed above. The right figure is a recent work by Vincent Joly and co-workers. They collected a massive amount of data from very different magnetic materials and plotted the reduced energy barrier of the creep law as a function of the reduced magnetic field. Once the depending energy and depending field of a given material are determined experimentally, you can see that all the curves follow exactly the same slope, confirming the validity of the creep regime for materials with completely different macromagnetic parameters. This shows beautifully the robustness of the universal scaling. I'd like to come to the last part of this lecture and discuss the motion of magnetic objects beyond one dimension. So in other words, I'd like to understand how magnetic bubbles and skyrmions can be set in motion and how this motion works. To do that, I will introduce an idea that was put forward by Thiele and that consists in assuming that the motion of this magnetic object is rigid, so not much deformation, and in this case I can transform the Landau-Lipschitz-Gilbert equation into a Newton equation. How do I do that? First, you might remember from the previous lecture that the magnetization is set in motion by a thermodynamical force, which is a variational derivative of the energy functional with respect to the magnetization. I can relate this thermodynamical force to the mechanical force associated with the magnetic energy. By definition, the mechanical force is the spatial gradient of the energy, which can be simply related to the variational derivative this way. Now, let me rewrite this expression using the Landau-Lipschitz-Gilbert equation, assuming rigid motion and in spherical coordinates. And this is what I get. Now, if I integrate the expression of the mechanical force over the volume, I'll have the definition of the mechanical force exerted on the magnetic object and sending it in motion. This equation is called Thiele equation. The first term is a driving force that can be either a field gradient or spin transfer torque. The second term is called the gyrotropic vector, and the last term is a dissipative tensor. Let's first neglect the gyrotropic vector. In this case, you see that the velocity is given by a balance between the applied force and the dissipation, which looks pretty much like the Drude model for conductivity. The gyrotropic vector has a very interesting role. You see that it involves the cross product between two spatial gradients, and as such, it only exists if the magnetic texture is two-dimensional at least. Actually, to ensure that the gyrotropic vector does not vanish, the magnetic textures must have some sort of topology, like in the case of magnetic vortices, bubbles, and skyrmions. In Thiele equation, this gyroscopic vector acts through a cross product on the velocity, which means that it mixes the velocity components that are longitudinal and transverse to the applied force. In other words, this term induces a deviation of the velocity direction transverse to the applied force. In other words, it induces a Hall effect. Now let's look at a couple of examples of the motion of two-dimensional magnetic objects. We start with a magnetic bubble in permalloy, studied by Finizio and co-workers. In this work, the authors used a magnetic field gradient to move the texture. Why magnetic field gradient? You might remember from a previous lecture that in the Stern and Göhler experiment, it was shown that a magnetic field gradient couples directly to a magnetic moment. And in a sense, a magnetic bubble is nothing but a magnetic moment embedded in an otherwise uniform magnetic landscape. Therefore, a magnetic field gradient moves the magnetic bubble as shown on the top picture. Now, if you apply a high-frequency magnetic field gradient, you can set the bubble to rotate as shown in the bottom picture. This rotation directly comes from the gyrotropic vector in Taylor's equation. This rotation demonstrates that the magnetic bubble is a topological object. A somewhat similar experiment was performed in Matthias Clauey's group on a magnetic vortex wall. Here they use spin transfer torque rather than a field gradient. We haven't discussed about this fascinating mechanism yet, but in a nutshell, you send a charge current through the structure and it exerts a torque on the vortex. Again, you see that if you inject a high-frequency current, the vortex is set into rotational motion, pretty much like the magnetic bubble, revealing the presence of the Hall effect. An explicit measurement of the Hall effect has been performed by Wanjun Jiang on metastable skyrmions. Here, the skyrmions are obtained in an ultra-thin multilayer, and a current is injected along the wire. At low current densities, you see that the motion is mostly longitudinal. It scatters a little bit due to disorder and grain boundaries, but there's no overall transverse motion. However, above a certain threshold, a clear transverse motion is observed. Phenomenologically, you can see those two regimes as arising from a balance between the pinning force and the external force. As long as the external force is not too large, the disorder averages out the Hall effect. But when the force is large enough, the disorder is much less influential and the Hall effect becomes robust. The reason why domain walls on skyrmions have attracted massive attention in the Spintronics community is because of their potential for application. The most famous proposition is due to Stuart Parking, who invented the concept of racetrack memory. The idea is to use magnetic domain walls arranged on magnetic nanowires to convey bits of information, like in a shift register. In his proposal, the domain walls are moved by applying a charge current along the wire. One can imagine to build up dense arrays of wires to achieve non-volatile memory and data storage devices. This idea was extended to magnetic skyrmions in a recent paper by Albert Fert. The whole physics is the same, except that now you use very small skyrmions to store information. The concept of the racetrack memory has fostered impressive research effort in the community. The realization of room temperature magnetic skyrmions has also triggered extraordinary creativity. It has been recently proposed to use skyrmions for artificial synapses, or to use the complex patterns obtained in chiral magnets for reservoir computing. The game is now open, and many more exciting ideas are proposed on a daily basis. What I'd like to emphasize is that what makes this new concept technologically relevant is the possibility to control these magnetic entities using electrical currents. The physical mechanism involved in all these devices is the transfer of angular momentum between flowing charge currents and the magnetic texture. And this is really what Spintronics is about.
We have seen that we can manipulate magnetic domain walls using either external field or external field gradients. The manipulation of magnetic bubbles using external field gradients led to the discovery of the non-volatile magnetic bubble memories in the 70s. Actually, 20 years ago, it was realized that it is possible to manipulate magnetic domain walls just by injecting a charge current through them. The effect uses a mechanism called spin transfer torque. This leads us to contemplate the vast field of spin transport and current-driven magnetization dynamics, which lies at the core of Spintronics. This is going to be the topic of the next 4 lectures. Let's move on.